All right, let's talk about cloud-native network security. It can feel, incredibly complex. So today, we're going to peel it all back, layer by layer. We're going to go on a journey that starts way out on the public internet and travels all the way down into the very heart of the server, uncovering all the hidden defenses along the way. I mean, really think about it for a second. You tap a button on your phone and boom, something happens. It feels like magic. But what's really going on behind the scenes is that one simple request is kicking off this incredible chain reaction, passing through multiple, totally distinct layers of security. Each one has its own rules, its own gatekeepers, and, as we'll see, its own unique dangers. So here's our game plan for this explainer. First, we're going to get our bearings in this networking maze. Then we'll look at how we guard the front door to our systems, and then how we police the traffic once it's inside. And then things get interesting. We'll see how a security feature can go horribly wrong. We'll finish up by tuning the server's engine itself, and then see how this all fits together. Okay, to really wrap our heads around this whole networking maze, let's use an analogy. I want you to picture your entire cloud environment as a high-security corporate campus. Every single network request that comes in is like a visitor. It needs to be checked out, given the right badge, and escorted only to the specific room it's supposed to be in, and absolutely nowhere else. Our journey starts right where you'd expect, the main gate, the very edge of our campus. This first layer of security is all about managing who gets to come in from the big, wide world. This is your front desk, your security team. It's the first checkpoint for every single visitor.
Now, in networking terms, we call this north-south traffic. Just think of it as any communication that has to cross the border of our Kubernetes cluster. It's traffic coming from the north, the public internet, and trying to get south into one of the services running inside. And managing that flow is the whole job of our front door.
For a long, long time, the way we handled this was with something called the Kubernetes Ingress API. And it worked, but it was pretty limited. It was mostly just for web traffic, and it got really messy with different vendor-specific settings. The modern way, the better way, is the Gateway API. And this is a huge step up. It's way more flexible, it can handle all kinds of traffic, and it's portable. It's a powerful, standard way to manage that front door, no matter where you're running your stuff. Okay, so our visitor made it past the front desk. They're inside the campus. Now what? We can't just let them wander around wherever they want, right? Of course not. They need a key card that only lets them into the specific rooms and hallways they have permission for. And that brings us to our second layer of security, controlling movement inside the building. This internal chatter, this is what we call east-west traffic. It's all the communication happening between your different microservices. The back end talking to the database, or the login service checking with the user profile service. It's all the crucial conversation happening inside the walls of the cluster. And listen, this is one of the most important things to understand about Kubernetes. Out of the box, by default, the inside of a cluster is a total free-for-all. Any service or pod can talk to any other pod it wants. Now, that's super flexible when you're just getting started, but from a security perspective, it's a nightmare. If one single service gets compromised, it has a wide open path to attack everything else. So how do we fix that? Well, this is exactly what Kubernetes network policies are for. They are, quite literally, the digital keycard system for our campus. With some pretty simple rules, we can define exactly which services are allowed to talk to each other. We can lock things down so the front end can only talk to the API service, and the API service can only talk to the database. Period. This is how you enforce that principle of least privilege and seriously limit the damage an attacker can do.
Okay, now for the twist in our story. We've secured the front door. We've issued key cards for all the internal rooms. We should be pretty safe, right? Well, what about the wiring inside the walls? We're going deeper now, down to the virtual switch that connects everything together. And this is where a security feature, something designed to protect us, can be flipped on its head and turned into a powerful weapon.
To get what's happening here, you gotta understand a classic old-school network attack called a MAC flood. Basically, an attacker just spams a network switch with tons of packets, and every single packet has a new fake hardware address. The poor switch tries to learn all of these fake addresses, filling up its memory with junk until it just gives up. And at that point, it panics and just broadcasts all traffic to everyone, which lets the attacker listen in on everything. And the fix for this has been around forever. It's a feature called port security. You just tell the switch, hey, only listen to traffic coming from this one specific whitelisted address. Problem solved, right? Well, no. This is where things get wild. In the world of virtual networking, using something called Open vSwitch, or OVS, this exact security feature backfires spectacularly. When an attacker sends a packet with a fake address, port security kicks in and tells OVS to block it. But here's the fatal flaw. OVS blocks it by creating a brand new, very specific rule to drop traffic from that one fake address. So when the attacker sends another packet with another fake address, OVS has to create another new rule. One malicious packet forces the creation of one new rule. So why is that a big deal? Because OVS has a limit. It can only hold about 200,000 of these rules. An attacker can easily, almost trivially, generate 200,000 packets with random addresses, forcing OVS to create a new rule for every single one, and completely exhausting its capacity. And the result is just kind of brilliant in a terrible way. You get a massive denial-of-service attack. The very feature that was designed to stop the switch's memory from overflowing is now the direct cause of it overflowing. This chews up tons of CPU and memory and can bring the entire node to its knees, all because a security feature was used in a way its designers never intended. Wow, okay, we've gone from the front gate, through the hallways, deep into the wiring in the walls. Now we're going to the deepest layer of all, the foundation of the building itself. We're talking about the host operating system's kernel, and how this is configured is absolutely critical for the performance and stability of everything else. Down at this level, we're not really talking about security rules anymore. We're talking about tuning the engine of the server. For instance, we can adjust how much memory the system puts aside for network traffic so it can handle huge data transfers without choking, or we can switch out the algorithm it uses to handle network congestion for something more modern, like Google's BBR to slash latency. This is the deep, nitty-gritty optimization that makes sure our foundation is rock solid and fast. So we've taken this incredible journey from the edge of the internet all the way down to the server's core. And if there's one thing we've learned, it's that cloud network security isn't just one thing. It's a stack. You know what? It's a layer cake. Every layer has its own job. The Gateway API, that's our main gate. Network policies are the internal keycards, keeping things separate inside. The virtual switch, that's the wiring that connects everything. And as we learned, it can have some hidden flaws. And finally, the host kernel. That's the foundation the whole building sits on. A weakness in any one of these layers can put the entire system at risk. The big takeaway here is that defense in depth isn't just some buzzword. It's an absolute necessity. You have to think about security from the top all the way to the bottom. Which leaves us with one last big question. Is your network secure at every single layer?